The idea is to look at those situations and make some conclusions about just looking at, like, kind of making observations and conclusions kind of the ones. We'll talk about it later. Okay, so when you're looking at all those ones in the bottom part, you're relating them to the ones in the top. So any observations about this value? So it's like we're looking at the two vectors, and then we're saying, okay, here's the value of the dot product, which is just a number. What observations, specific observations, did you make about that value of the number based on the two vectors? Alyssa?
When the vectors are perpendicular,
Okay, that's good observation. Did you see that? If your two vectors are perpendicular, then the dot product is 0. Okay, what else? Yeah, Christian?
The dot product is negative if the angle between them is greater or opposite.
Okay, so it's like kind of like if there's a component of one in the opposite direction of the other, then you get a negative dot product. Great observation. More? Others? Yes, sir?
If they're parallel, the dot product is just both their magnitudes multiplied together.
More specifically than parallel. Because there's two ways to be parallel, right?
Yeah.
So which way do you mean?
Well, if they have the same angle.
Same direction, right? Exact same direction. Then the dot product is product of the magnitudes. Another observation. What else? How about, let's do the other case. What about exactly in the opposite direction? What do you get for the dot product when they're exactly in the opposite direction? Yeah, yes, sir.
You get the magnitude of the two dot products, but always in the negative direction.
Okay, but the dot product is just a number. So what? Tell me about the number that is the dot product. If negative of what? Negative what's the value? Then the opposite.
Of the magnitude.
Product of the magnitude. Yeah, you can say. Yeah. So if they point in the opposite direction, I can't really get my hands to do it. Oh, almost. There we go. Then you get the opposite of the product of the magnitudes. Did we hit all? There's one more case that we didn't hit there. What about if they're kind of generally in the same direction, like one has a component in the same direction as the other? Then what? Yeah. Okay, it's acute angle. What about the value of the dot product? Yeah.
Positive.
Positive. And how does it? It's positive, and how does it compare to the product of the magnitudes? He wants less than. Agree with that? So if they point in the same direction, we get the product of the magnitudes. If they kind of point in the same direction, then you get something less than that, right? And if they're perpendicular, then you get 0. And if they kind of point kind of away from each other, you get a negative and perfectly away from each other. The opposite of the product of the magnitudes. Okay, so let's summarize. So if they have the same direction, what do we say? You get the product of the magnitudes for the dot product. When they have the opposite direction, can you read it in the back? Okay. You get the opposite of the product of the magnitudes. When they're orthogonal, two vectors are perpendicular, we call that orthogonal. So perpendicular is kind of the physical representation of orthogonality, like they're at a pi/2 angle, or 90-degree angle. When you get into higher dimensions, it's hard to imagine perpendicular, so this term orthogonal has the same mathematical meaning as that, okay? So perpendicular is like the spatial or the physical representation of this mathematical principle, orthogonal, okay? 0, right? When A has a component in the same direction as B, meaning the angles are acute, the angles acute when tail to tail, then we said that the dot product is, what do you say? Positive, but less than the product of the magnitudes. Positive, but less than the product of the magnitudes. Likewise, if A has a component in the opposite direction of B, negative, but less negative than the opposite of the product of the magnitudes. And if we're in oh, I missed one. Oh, I got it over there. Okay, so this is all the cases, right? This is all the possibilities. So if we can we put this all together and kind of really concisely come up with a value for this, a value for the product of the magnitudes? Is there some common thread here? When we say the value of the product dot product is what? Christian?
The product of the magnitudes multiplied by the cosine of the angle.
Okay, so that's a way to find it. That's another way to find the value. What is that getting at? So it's the common thread here. What is this? The product of the magnitudes, right? The product of the magnitudes. But then how does direction play into it then? So how can we qualify that? Yeah.
How much they're in the same direction?
Is it how much they're in the same direction? Isn't that true? Because if they're totally in the same direction, what do you get? You get the product of the magnitudes, right? And the more that or the less that they're in the same direction, that value goes down until they're what? What's orthogonal? Perpendicular means how much are they in the same direction if they're orthogonal? They're not at all, right? They have perfectly not in the same direction. That's what orthogonality is. So you get 0. And then you have the same kind of idea pointing in the opposite direction, but then all the values are negative. So we can say that the value of the dot product is the product of the vector's magnitudes, but as much as what? As much as the vectors are? Say it. Some of you are whispering it. Only as much as the vectors are in the same direction. Super huge concept. So this number that you get when you do the dot product, it is multiplying the vector's magnitudes, but only as much as those vectors are in the same direction. So if they're not in the same direction, you get 0. If they're in opposite directions, you get the product of the magnitudes, but the opposite of it. Okay, and then so Christian pointed out that that's the same as taking magnitude of A times magnitude of B times cosine theta, right? Cosine of the angle between them does this very thing. It takes as much as one is in the direction of the other times the other, right? So huge. So this is when things get real hairy and hard at the end of the semester, and we're trying to conceive all these vectors in 3D. This is going to be it's going to frame some important concepts, okay? So it's the product of the vector's magnitudes, but only as much as the vectors are in the same direction. Okay, cool. So now we're going to start doing work this semester. Yeah?
I'm just confused. Is cosine arbitrary? Like, can you use sine, or is it always cosine?
Will sine do this? Right? So that's the question. Will sine do this? Will it give you... So cosine theta, what will cosine theta give? So if I have the magnitude of A and the magnitude of B. What does cosine give and what does sine give, right? So if I take are those
Okay.
different, or is it arbitrary? Because this will be what? Oh, yeah. So like if you made this your x-axis along B, if you made it your x-axis, then what would you get? Magnitude of A cosine theta would be this much right here. And what would Magnitude of A sine theta B. Okay, so it doesn't matter? Yeah, because it's the product of the magnitudes in as much as they're in the same direction, not in as much as they're orthogonal, right? If it's in as much as they were orthogonal, then you'd have that. So it's important. It needs to be cosine. Other questions? Okay, so now we're going to start doing work in the course. Bad joke. We hadn't done work yet. Now we're going to do work. So work is defined as the total amount of force applied over a distance. They pay me to teach, not to make jokes. All right. We can investigate the amount of work to move an object, a scalar quantity, by observing the force applied and the displacement of the object. So force and displacement are vectors, but work is a scalar quantity. Work is the amount of work to move it's the amount of force applied over a distance, okay? That's what work is. All right, so let's look at a real simple example here. So a girl pulls a wagon with a force of 56 newtons at an angle of 39 degrees above horizontal for a distance of 8.1 meters. What's the work applied to the wagon by the girl? So here she is. And so we can imagine vectors. So we can imagine the force that she's pulling, 56 degrees or 56 newtons, at an angle of 39 degrees above horizontal. And then, so that's the magnitude, right? So the magnitude of F is 56 newtons, and the magnitude of D is 8.1, and I'm showing as arrows, I'm showing their directions, right? So can you write vectors F and D in component form? Can you write vectors F and D in component form? We should be able to. All right, Alexandria, you pick either one. Tell me either F or D in component form. Can you tell me either one of those? Okay. How about Shane? Take a pick. Right, vector F or D in component form. Take your pick. So the two sets of Weber problems that we've done so far, all about just learning the ins and outs of vectors. It's kind of all for naught if we can't do this. Ada, you take your pick. What's that?
D is 8.1, comma 0.
Right. 8.1 comma 0 would be the vector D. You want to do the other one?
And then F is just 56 cosine 39 for X, and then 56 sine.
Right. So it'd be 56 cos 39, 56 sine 39 would be the vector F. And vector D would just be 8.1 comma 0. Right? Component form means you got your component in the x direction and component in the y direction, which are D you can think of as changes. Yes, sir?
How can we use the force and the meters as like two parameters of it? If you're like imagining it on a grid, the meters is one scale of like distance on the grid.
Oh, nice. Okay. Yeah, that's good.
Is a different unit.
That's good. Yeah. So I drew them here in the same picture, but they're really different units. Exactly. So so it's kind of just, I guess we just have to superimpose the two planes on top of each other, like a distance and the force plane.
Okay. But that gives you like vectors in the same scale?
Yeah, I mean, you know the answer to it. The 56 is in terms of newtons, and the 8.1 is in terms of meters. So a visual representation, you just have to...
But if you're going to solve it, like, can you do it like that? Because
yeah, we're not... Oh, so yeah, we're not going to... we're not going to solve this like by like adding or subtracting these vectors, right? Yes, right. So if we were coming to add or subtract these vectors, we'd have a problem because we're adding apples and oranges. So yes, good point. But we don't have to add these, right? So we're not going to add these. So let's talk about work here. So F is that and D is that, we said, okay? So which component of F contributes to the work done? X or the Y component? X component. Y. So you see that the Y component of this force has nothing to do with the work to move that wagon. Is that fair? So then we can do it now. So if work is force times distance, what are we going to multiply? Force times distance. So we're going to multiply. What's the force? 56 cosine 39. Distance is 8.1. So just force times distance. Our force is just the X component of F, and the distance 8.1. So you get 352.5 joules. So notice that the work is what? It's the product of the magnitude. So really we multiply 56 times 8.1, but only as much of the 56 as was in the same direction as the 8.1. Do you notice that? We only multiplied as much of the 56 newtons as was in the direction that we moved the wagon. Well, that should ring a bell. What is that? That's the dot product, right? That's exactly what the dot product does. It will take as much of that in the direction of that and multiply them together. It'll multiply the 56 times 8.1, but only as much of the 56 as in the direction of the 8.1. That's dot product. All right, so this gives us an alternate way of finding the dot product, which we already talked about, right? So the product of the magnitudes times the cosine of the angle between them. So that's an alternate way of solving it than the way like you did for the worksheet, right? So the worksheet, you had this algorithm where you multiplied the X components and the Y components and you added. Well, that gives you the exact same value as multiplying the magnitudes together and times the cosine of the angle between them when they're tail to tail. This is the angle theta. So that means, since they give the same value, that means we can calculate the work by that algorithm that you did for the homework. Make sense? Right? Because you get the same value whether you do it the homework way or you do it using the cosine. So that means if you want to find the work, you can do it by doing it the way you did in the homework. Multiply like components and add. Because it's the same, you get the same value. So what would that look like? So here's F, and here's D, and so what would happen when we multiply like components and add? You get the same thing. You see that? You're going to do the X times the X plus the Y times the Y, and you're going to get the exact same value. So the moral of the story is there are two ways to compute this value of the dot product. There's the way that kind of encapsulates our meaning for the dot product. Which way is that? What's the way of calculating that kind of embodies our understanding of the dot product? Which way is that? Yeah. Using cosine, right? Using cosine. When you do F, the magnitude of F and the magnitude of D times cosine theta, that embodies our understanding of dot product, that it's product of the magnitudes and as much as they're in the same direction. Okay? But the other way is just as a legitimate way of calculating that value. Product of the x's plus the product of the y's. And then if you're in R3, plus the product of the z's. Okay? So, which way do you use? Whatever's most convenient in your given situation. So you always just use whatever is the most convenient thing at your fingertips, given what you have in the givens. Don't feel like you have to use one or the other. They give you the same number, so use whatever's most convenient. Okay, notice then it also becomes a way of being able to calculate. You see that this gives you a way of being able to calculate the angle between two vectors. If you knew what the vectors were, could you find each of the magnitudes? And you knew what the vectors were, so you could do the dot product the homework way, the worksheet way, and you have the magnitudes, and you could solve for the angle between the vectors. Do you see that? I can see lots of yeses. Does it make sense? If you have the two vectors, then you can find the dot product by the worksheet way. You can find the magnitudes, and that allows you to solve for the angle between them when they're tail to tail. Okay, so here's a practice problem. How much work is done to push a box from point -210 up the ramp to point P shown if you're applying a force of 8, -15, 0? So so this will be so there's Newton meters, that's joules for work, and then there's foot pounds is the English unit for work. So this will be foot pounds because we got all our coordinates in feet and our force in pounds. So how much work to push the box up from -210 up the ramp to point P? If the force applied is 8, -15, 0. So I'll let you think about that. You found what?
From the initial point to the P.
But what did you find? You found. I didn't hear what you said. You said you found the.
Like this is like the segment from the initial point to P.
-2. So it's kind of like down here, at this corner of the ramp. And so what did you find it to be?
-1, -7.
-1, -7. And what is that called?
From that point to P.
Yeah, what is it? What is it from that point to P?
The distance.
Not the distance. It's not the displacement. Oh yeah, because it's a vector, right? Yeah, so that's the displacement vector. Okay? So how are we gonna find the angle between these two vectors? How are we gonna find theta? What's that? You don't have to. Why not? Right. Force equals, or work equals, force dot. So there's a real easy way to do this and a really, really hard way to do this, right? Did you find the easy way? What do you do? Well, yeah, the dot product, but how? Yeah, do the way you did on the worksheet, multiplying components and adding, and then it's a piece of cake, right? Force is 8, -15, 10, or yeah, 0. Displacement is -1, -7, 2. Is that right? For a total amount of 97 foot-pounds. So even though we didn't do force times distance per se, like how much force there was in the distance, right? That would be more like the cosine way, cosine theta. It's still, the dot product is still the amount of work. So you can do it this way. And it gives you this is the same as the amount of F in the direction of D. So it's still force times distance. It's still the amount of F in the direction of D times D, the distance. Any questions on that? Does it make sense? Okay, let's talk about projections. Projections. So there's something called the scalar projection and the vector projection. So if we're talking about B, so there's the projection of B onto A and A onto B. So for our purposes here, I'm going to do B onto A. So the projection, scalar and vector projection of B onto A would be, the scalar projection would be looking at how much of B is in the direction of A as a scalar, just like as a magnitude, right? So I want to know what's that length right there if we're drawing it. What is that length right there? So that's the scalar projection of B onto A, and so we should all be able to do that. I want to write what that length is. What do you think? The x component of B. He wants, so B cosine theta?
Or like the magnitude.
The magnitude of B times. Does everyone see that that's exactly what that is? That length is the magnitude of B times cosine theta. But what does that almost look like? That's almost what? The dot product, right? So how could we write it in terms of the dot product? So if I wrote the dot product, what would I have to do to the dot product to get that? Divided by magnitude of A, right? Doesn't that make sense? If I took the dot product and divided by magnitude of A, I would have the same thing as that, right? Because the magnitude of A would go away. Follow? Okay, so this is the scalar projection of B onto A. Or the amount of B in the direction of A, right? The amount of B in the direction of A. So it makes sense that it has to do with dot product because dot product is the product of the magnitudes as much as they're in the same direction. So this is just saying, what's the amount of one of those vectors in the direction of the other? Okay? What about the vector projection? Well, the vector projection would be that vector, what I'm showing in gold there. So this is a little more challenging, but we can still do it based on what we know so far. Can you write that vector? Can you define that vector right there? Any ideas? You have all the tools. You have everything you need. So what do you notice about that vector?
It's in the same direction.
Same direction as A. So what? It's a scaled version of A. How do we get scaled versions of A? What do we do? So how do we get a scaled version of A? What do we do?
First, you find the unit vector of A.
Okay.
We're in the direction of A.
But just very in general, not this particular, but just how do we get a scaled version of A? How do we get something in the same direction of A with a different magnitude? Just multiply by scalar multiplication, right? So I'll just call it K. So there's we're looking for some scalar K times A that's going to give us that vector, right? I'm just rescaling the vector. Okay? So the question is then, what's that? So some of you are talking about the unit vector, right? So if I had the unit vector in the direction of A, which is A divided by, that's the unit vector in the direction of A. And how do I get it to be the magnitude it needs to be? What's that?
Times the length.
Yeah, what's the length? What's the length?
Scale.
The scalar projection, right? So if I got the unit vector in the direction of A, that has magnitude 1. If I scale it by this much, I'll get that gold vector. You see that? So I'm just going to take this. I'm just going to put it right there. So I'm going to scale the unit vector in the direction of A by the magnitude that I want. So this is a scalar, right? This is a vector, a unit vector here. This is a scalar. So then we can rewrite that. I can combine these magnitudes of A, and I can make my scalar A dot B over the magnitude of A squared. That's my scalar. Times A. So that's the scaling factor on A that's going to get me the right length. And so then to remember B onto A versus A onto B, I think onto A is in the denominator. Right? So this whole stuff is on A, on top of A, right? So if it was A onto B, then you know that your magnitude of B would be in the denominator. Right? Everything would be flipped. Okay, questions on that? So let's summarize the formulas here. So the scalar projection of B onto A, this is what you'll see for the notation. Component of B onto A. That's that. That's the scalar projection. And then the vector projection is projection B onto A. Exactly what we said. So something to think about. How could you find this vector? That's the easiest way. Now to get this vector, this blue one. So you're thinking about sine, right? But now that I have this, it's a lot easier than using sine. Anyone see? If I have this vector, I have the vector B, right? And I have the gold vector. Yeah. Okay, so that would be the relationship of the magnitudes. But what about just the vectors themselves? What's that? Okay.
B is equal to the gold one plus the blue one.
Right, this is just vector addition, right? Don't we just add these two vectors together? And if we add those two vectors together, we get B. So the blue one is what? B minus the vector projection onto A. You see that? So this vector projection, it's really about finding components of B. Instead of x and y components, they're components of B relative to A. See that? So the vector projection is like the parallel component to A, and then once we have that, we can easily find the perpendicular component to A just by simple vector addition. This plus this equals that. Do you see it? Okay, so now I'm not going to do any examples, and so this is where some problem solving comes in, but when you're doing the homework, be on the lookout for ways to apply this. The scalar projection, the vector projection, it will make your solving process a whole lot easier than if you didn't know this. Okay? So just you have to really, when you get some of these application problems, be on the lookout for ways to use the projection formulas. So you're given these situations, you've got to draw pictures and think about creating vectors in lots of places to see what's going to help you, right? This is about vectors. So you're going to draw pictures of the situation, then draw vectors that are helpful, and then look for ways to apply the scalar and vector projection. But I don't want to do them because then you end up just doing them with different numbers, right? So there's a problem-solving aspect to it. So I want to let you grapple with that. So you've got the tools. It's just keep your focus on vectors and look for chances to apply this projection formulas, okay? You can do it. All right, let's talk about. So with vectors, there's 3 types of multiplication. Scalar multiplication. Scalar multiplication multiplies a what by a what and results in a what, okay? And what's the meaning of scalar multiplication? Dot product multiplies a what by a what and results in a what? And what's the meaning? So I want you to take 2 minutes to talk through, fill in the blanks, and review the meanings of scalar and multiplication and dot product. So everyone's got a partner or a group of 3, and you're going to have a little little discussion. Go. So did you say a scalar, it multiplies a scalar by a vector and results in a vector? Agree? Okay, and so then what is that vector, Megan? What's the meaning of that? The meaning of the resulting, what's that? Right. And what about the direction of the new vector? So yeah, so you enlarge it or you shrink it, and then what about the direction of the new vector? Same, or it could be opposite direction if your scalar is negative. Okay, dot product. Yanni. Yep, and what about the meaning of that? What is the meaning of the, so the scalar that you get, the dot product, it means what? What is that? Yeah?
The magnitude of the, like, direction of the other, I don't know, that's hard to explain.
Yeah, so there's kind of a baseline meaning to it that's qualified, right? And we got to get that baseline meaning down. What is, in essence, what is the dot product? Yeah, Alyssa.
The product of the magnitudes in the same direction.
Yeah, so the core principle is it's the product of the magnitudes. It's the product of the magnitudes, but it's not just the product of the magnitudes, right? Only so much as they're in the same direction. Only as much as those vectors are in the same direction. So you get like, you're getting like a part of the product of the magnitudes. The part that's equivalent to how much they're in the same direction. Okay, but first and foremost, it's the product of the magnitudes. It's a product. It's a product. So you're multiplying the magnitudes together, but only as much as they're in the same direction. All right, so then there's a third. Cross product. The cross product, wonderful, multiplies a vector by a vector and gives another vector. Okay? So cross product is the third type of multiplication, and you multiply a vector by a vector, resulting in another vector, a third vector. So you're going to have the same kind of deal for homework with a sheet, so let's take a look at that, and I'll get you started here. But I will post it on Blackboard. You can print it out and do it, but we'll get started. So here's the sheet. Now here it's R3 is key. All right, R3 is going to be important for cross product. So I'm giving you first of all there's 7. Kind of the same as the worksheet for dot product. There's 7 kind of starting examples, and I actually give you the answer. So here you're not going to be calculating according to an algorithm I give you. These first 7 we're just going to sketch. So let's look at this one here. So first we're going to sketch -2, 1, 0. So -2 means 2 in the x, -2 in the x direction. 1 in the y. So that puts me at this point right here. There's -2, 1, 0. And then -3, 0, 0 would be back here. So those are both, in this case, those are both in the xy plane. And then the resultant of the cross product, the resulting vector, is 0, 0, 3. So 0 in the x, 0 in the y, and just up 3 in z. So I'm telling you the answer. I'm giving you the 2 vectors, the cross product, and I'm telling you what the answer is. Okay? So you're going to do that 7 times, where you're going to sketch out, make sure you have some way of distinguishing between the 2 original vectors and the cross product. So I've got colors, so if you've got colors that could help, but some way you've got to know what you're looking at in terms of the two that you're crossing, and the result. You're going to do that 7 times. And then, based on those 7 times, now you have all these ones below in your worksheet. You're going to draw the first 2 the same way I draw the 2 red ones. And then try to look for one that's similar to one of the first 7 and see if you can guess it. So I'm not asking you to do any math. You're trying to make your best educated guess on what the resulting cross product would be just by studying the first 7. Okay? You're not going to get graded for your accuracy. Okay? Maybe completion. You might turn it in. Make sure you tried. But this is about trying to figure out what the cross product is about. Okay? So I wouldn't expect anyone to get them all exactly right. But you're making observations on the first 7 and trying to then apply those observations and maybe predict what they might be for the ones on the bottom of the page.